Alright, welcome everyone. In this video we're doing a 16.3 style problem. This is from fall 2016. We're doing problem number 4, and again 16.3 is talking about this fundamental theorem of line integrals. And this is really the upgraded version. This is something closer to what we may have seen in 16.5, but again it is the fundamental theorem of line integrals, so okay. Alright, so the first thing we want to do is compute the curl. And actually looking at this problem overall, we can kind of identify what we hope the curl is, right? So once we know the curl, part B is to actually find a function so that the gradient of that function is our vector field, so that's called a potential function. And then finally we want to compute a line integral. So remember, this kind of looks like the fundamental theorem of line integrals, and so we hope that our vector field is conservative. The only way that our vector field is conservative is if this curl is equal to the vector 0. So that's our hope, and this is a nice way to double check our work here. So let's go ahead and compute this. Remember, the curl is going to be del cross f. So we're going to have i's, j's, k's, the partial with respect to x, the partial with respect to y, the partial with respect to z. That's the del piece. And then let's go ahead and put our f. So our f is y squared z cubed plus 1. That's the first coordinate. Our second coordinate is 2xyz cubed. And then our third coordinate is 3xy squared z squared. Alright, and whenever we take a cross product here, we're going to have stuff with i's minus stuff with j's plus stuff with k's. And I just remember that I do this first just so I see the plus minus plus. Alright, again we're hoping for the vector 0, so to some extent I hope it doesn't super matter. Alright, so if I go ahead and cross off this first row and first column sort of deal, I'm going to have the partial with respect to y of our third component. So let's see, this is going to be 6xyz squared. So again, I did the partial with respect to y of our third component. Minus, we're going to do the partial with respect to z of our second component. So the partial with respect to z, that 3 is going to come down, and I'm going to have minus 6xy. And when that 3 comes down, I'll have z squared. So again, we see these perfectly line up, and indeed I get out 0. Okay, for my second component of my curl vector, right, I'm going to cross off the first row and the second column. So I'm going to be taking the partial with respect to x of 3xy squared z squared. So that's going to give me 3y squared z squared. And then I'm going to go ahead and subtract, let's see, the partial with respect to z of our first component. So that 1 goes to 0, and let's see, the partial with respect to z, so that 3 comes down, so I have 3y squared z squared. Thank goodness. So I get out 0. And then finally, if I do my third component, right, so I'm crossing off the third column, first row, I'm going to take the partial with respect to x of my second component, so that's going to be, let's see, 2y z cubed. And then I'm going to take the partial with respect to y of my first component, so that's going to be 2y z cubed. Thank goodness. So those perfectly cancel out, and I get 0 for my third component. So I indeed get the curl vector 0, 0, 0. Which means, hey, I have a conservative vector field, and therefore we should be able to find a potential function. Okay, so for the potential function, remember this is going to be f sub x, this is going to be f sub y, this is going to be f sub z. That's the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. So if I'm interested in finding f, right, I'm going to go ahead and integrate maybe my first component, my y squared z cubed plus 1. I'm going to integrate that with respect to x, because again, that's the x derivative, and so if I want to get f, I want to get back to where I started with, I'm going to integrate with respect to x. So when I do that, let's see, I'm going to have a xy squared z cubed, so again, all of this is constant with respect to x. Oops, there we go, z cubed. And then I'm going to have plus x plus a constant of integration. But remember, constants with respect to x could have y's and they could have z's in them. All of those are constant with respect to x, so they could have y's and z's. Let's go ahead and take the derivative. Again, this is my proposed f right here. Let's go ahead and take the derivative of this with respect to y, and I'm going to get 2xy z cubed, let's see, plus 0, plus, and this is going to be the derivative of the c function with respect to y. Remember, f sub y, that should be equal to my second component. So I'm going to go ahead and set this equal to this 2xyz cubed. 2xyz cubed. And so you can see there's a bit of cancellation. And so our partial derivative, c with respect to y, this is just equal to 0. So that means, right, if the derivative is 0, this must have been constant with respect to y. So actually, our constant function, c of yz, again, it could have y's and it could have z's in it. Actually, we know since the derivative of that with respect to y was 0, it doesn't have any y's in it. So it's just a function with respect to z, maybe. So let's go ahead and take the derivative, again, of our proposed function, our proposed answer here. We're going to take the derivative with respect to z now. So again, I'm going back here, taking the derivative with respect to z. So I'm going to have 3xy squared z squared. The derivative of x with respect to z is 0. The derivative of c of yz, again, this is really just c of z. If I take the derivative of that with respect to z, I'm going to get c prime of z. Again, just z's in there, so we can use the prime notation. And that should be equal to my third component. So 3xy squared z squared. 3xy squared z squared. And so again, we can see that these perfectly cancel out. We get, plus 0, so c prime of z is actually equal to 0. So the derivative is 0. That means it must have come from a constant function, right? If you were to just integrate this, we would get c of z is some constant. I don't know what it is, but it is indeed a true constant in this case. And so therefore, my function, my f here, again, going back to this line, is xy squared z cubed plus x plus a true constant of integration. And I'm sure now that there are no y's, there are no z's, anything like this. Just as a side note, I mean, for a lot of these problems, right, the majority of the points is in the work. So even if you were to integrate this and if you were to just put c and kind of go on your way, you would say, well, I got the right answer. It happened to be the correct answer, but you didn't show this process. So I've seen actually people get marked off for this. And so I just wanted to give you this heads up, right, that you do actually need to go through this entire process, even though in this case it happened to be the correct answer. If you just put this plus c, it's not guaranteed, right? There's still some flaw in the logic, and so you do have to double check. All right, so now we know our potential function, our little f. We would like to evaluate out this line integral. So our f was already given to us. Our curve here is the curve shown below, but they haven't told us how they parameterize this. This is a very interesting curve. The main things that I know is that it goes from 1, 0, 1 to 2, 2, 2. And luckily, thanks to the fundamental theorem of line integrals, I know that this is going to be f of b minus f of a. So remember, b is our ending point, a is our starting point. So that's going to be f of 2, 2, 2 minus f of 1, 0, 1. So f of 2, 2, 2. I go back here, and I guess as a quick side note, right, second side note maybe, it does say find a function, right? In particular, I want to emphasize a function, right? So in this case right here, this is the most general potential function, but we don't want we don't need the most general potential function. We can just do any old function. So in particular, I'm going to be using xy squared z cubed plus x, that is choosing my c to be equal to 0. You can choose your c to be 5 or negative 100 or whatever you want. All of them will yield the same result, remarkably enough. So I'm going to go ahead and choose the nicest one. So if I go ahead and I plug in 2, 2, 2. So 2 for x, let's see, that's going to be 2 times 2 for y. Y has to be squared, so that's going to be 4 times, z cubed, so z is also 2, so 2 cubed is going to be 8, plus x, so x was 2 in this case. So here is my f of 2, 2, 2, and I need to subtract away from that f of 1, 0, 1. So the fact that y is 0 is going to kill off that first term, right? So I'm going to have just 0, and then plus x. right? So again, my function is xy squared z cubed. The fact that I have a y in this first term, that makes it 0, plus x, so x is 1 in this case. So let's go ahead and multiply this all out. This is going to be 8 times 8, so that's going to be 64 plus 2 minus 1. So I think altogether we get out the answer 65. All right, so I got out the answer 65. I'll also highlight my other answers, right? We only need a function, and we were hoping that the curl was 0, so that way we have a nice conservative vector field. All right, that is it for this question. I hope you guys enjoyed, and I'll see you next time in 16.4. We'll talk about Green's theorem. I'll see you then.